Hello, my name is Brian Crafton, and I will be presenting our work titled Hardware Algorithm Co-Design, Enabling Efficient Event-Based Object Detection. My co-authors are Andrew Paredes, Evan Gebhard, and Arijit Ray Chowdhury, and we are all from the School of Electrical and Computer Engineering at Georgia Institute of Technology. Event-based cameras, also called dynamic vision sensors, or DVS for short, have been around since 2008. Event-based cameras output pixel-level brightness changes only when changes or events occur. This is different from traditional cameras, which output brightness intensity for every single pixel at every single frame. So by only sensing brightness changes, these sensors have been able to achieve significant advantages, namely high temporal resolution, low power consumption, and lastly, high dynamic range. All of these features make them especially interesting for computer vision on the edge. In the figure shown here, we visualize a stream of these events as a 3D point cloud on the right and a 2D image on the left. But a drawback from converting our events to images is that we essentially ignore the timestamp, losing the temporal resolution. So our question becomes, how can we use state-of-the-art CNNs and keep the high temporal resolution? So our idea is to create multiple frames from the event stream and process them as a mini video. We show an illustration of this here, where rather than compressing all events together, we break our event stream into 12 frames. And from frames 1 to 12, we can see how the pedestrian car movement can be captured. To implement our algorithm at the system level, we designed a system on chip based on standard components like a systolic array and DRAM. But because event streams require special preprocessing, we also design a custom module for aggregating events and generating frames efficiently. We then compare this hardware against traditional accelerators for CNNs. We find that because the event-based camera has such low power consumption compared to our reference camera, the AR1335, and because the power consumption of running a small object detection network is low, we can obtain between 1.88 and 2.17x reduction in power while enabling new applications requiring the features of event-based cameras. To evaluate the benefits of using multiple frames per event stream, we evaluate power and detection accuracy for 1, 4, 8, and 12 frames. We find that although more power is consumed for the 12 frames, we can obtain up to 7.6% increase in mean average precision. And so in summary, event-based cameras are an exciting new research domain. They promise low power, high temporal resolution, and high dynamic range. In this work, we presented a new system design enabling 1.88x to 2.17x energy improvement using event-based cameras, and at the same time, we demonstrate new techniques enabling up to 7.6% average precision increase, all while using off-the-shelf computer vision algorithms and readily available CMOS technology.